everyone, Mrs. Patel Dane here for AP Chemistry. So today we're going to go over topic 7.6, Properties of the Equilibrium Constant. So in this lesson, you're going to represent a multi-step process with an overall equilibrium expression and then use its constituent K expressions for each individual reactions. So as we've seen before, reactions occur in multiple steps. So we've seen this before with Hess's law and with rate laws. On the first two equations are going to be the intermediate steps, and the second or last equation is the overall reaction. So what I want you to do is rearrange the first two equations as needed in order to match up with the last equations. Remember, you can actually rotate or switch the sides of the reactants and products, and you can also multiply the entire equation by a coefficient in order to make the coefficients match up. We will play around with the K values in just a little bit. So go ahead and pause and do that. All right, so as you went through, hopefully you saw on the left-hand side, we had N2 and O2 for the first equation. However, in the second equation, the NO2 were actually switched. So what we're going to do is switch or rotate the second equation. So we have 2NO plus O2 on the left-hand side, and then we put the 2NO2 on the right-hand side. We can get rid of that equation. So for the K values, if we switch the equations, we actually end up taking the reciprocal, which we haven't done before. So go ahead and cross out any intermediates and make sure that the reactants and products match up. So also in Hess's law and with rate equations, we saw that with their values, we would add them up. In this case, we're actually multiplying this intermediate K values. So we're taking KC1, which is 2.3 times 10 to the negative 19th, multiplied by KC2, which is now the reciprocal of 3.3 times 10 to the negative 7. So we can actually just take 2.3 times 10 to the negative 19th and put that over 3.3 times 10 to the negative 7th in order to get your overall K value. So as we do that, we end up seeing that we have multiple values in there. So it's 6.96 repeating. If we look, however, at the original numbers, we have to take a look at sig figs. So the first KC1 had 2 sig figs, and then KC2 also had 2 sig figs. So we're going to round the 6.96 to be 7.0, and of course match up the 10.13 for your exponent. So make sure you box your final answer. So essentially what happens to K or Q when you reverse a reaction? So if the reaction is reversed, you're going to take the reciprocal of K or Q. If you multiply by the coefficients by a certain factor, in this case, we would actually raise that Q or K to that specific power. Don't forget that whenever we have a coefficient for K or Q, we raise it to that power. So that's essentially what we're doing right here. And then when we put the intermediate reactions together, we end up multiplying K or Q values. So at this point, can you represent a multi-step process with an overall equilibrium expression using the constituent K expressions for each individual reaction? Have a great day, everyone.